Let's look at another specific example where we will use the guidelines mentioned to analyze and sketch this particular function. We begin by asking ourselves, what's the domain of this function? Remember, for the natural log function, we need the argument to be greater than 0. So we know that x is greater than 0. The domain of this particular function is the set of all x's such that x is greater than 0. Or you could express this as an open interval from 0 to infinity. Ask yourself if this function possesses any intercepts. We typically search for x-intercepts first. In order to have an x-intercept, we set the y value to be 0 and then solve that equation. We already know x can't be 0, so this second factor here must be 0. And we could solve this equation by looking at the natural log of x equal to 0. By the definition of a natural logarithm, e to the 0 power will get you x, so x must be 1. Therefore, the x-intercept is 1, 0 as an ordered pair. Since x can never be 0, there can never be a y-intercept. Ask yourself, does this function possess any symmetry? Is it even or odd? When you are seeking symmetry, we always observe f of the opposite of x. But remember, the domain is actually the positive x-axis, so seeking f of the opposite of x is not even possible. Therefore, there is no symmetry. F of x is not even, and f of x is not odd. Ask yourself, does the function possess any horizontal asymptotes or any vertical asymptotes? I recommend that you seek horizontal asymptotes first, as this coincides with the definition of end behavior of a function. We need to seek the end behavior anyway, so let's look at the left end of your particular domain. Remember, the domain for this function is actually the open interval from 0 to infinity. So we want to look at the left end. That means we want to look at domain values that approach 0 from the right. We want to ask ourselves, where do these y values go if x approaches 0 from the right? Now remember, for limits, you have to be 2 steps ahead, meaning you must be able to check its form. Now, what's very small times very large? That is considered an indeterminate form. When you have this situation, the best thing to do is try to utilize L'Hopital's rule. And how do we utilize L'Hopital's rule? With a little bit of algebra, we turn this function here into a fraction. If you could turn it into a fraction, then we want to try to evaluate the limit by being 2 steps ahead and check its form. When you check its form this time, we have very large in the negative direction over very large. That is still indeterminate form. But that allows us to use L'Hopital's rule, and that simplifies to be this expression here. Use a little bit of algebra, and you realize you will arrive at a determinate form very, very soon. Very small over 2 is a determinate form. In fact, that will determine to be 0. So the end behavior is actually a hole at x equals 0. At least the left end. There's also no vertical asymptote at the left end, and there's no horizontal asymptote at the left end. We still need to observe the right end of the domain. So we're going to observe the limit of the function when x approaches infinity. Check its form, be 2 steps ahead, and notice that is just very large. That is a determinate form, so we now could say that the limit as x approaches infinity does get to infinity, or I should say should approach infinity as well. Thus, at both ends of the domain, there are no horizontal asymptotes and there's no vertical asymptotes for this function. Why don't we utilize derivatives? Are there any intervals of increasing and decreasing? In order to do this, we need to take the first derivative and find critical numbers. For this particular function, the derivative requires the product rule, and inside that product rule, you will need to know the chain rule. The derivative rules need to be mastered and executed with precision in order to analyze functions. The first derivative looks like that, and then of course, if you can factor the first derivative, you want it in reduced factored form. This turns out to be a product of two factors. I'm going to circle this or emphasize it. That is the first derivative that will be used for the first derivative test. In order to use the first derivative test, you do need critical numbers. The denominator here is 1, so we only need to look for type 1 critical numbers. Type 1 critical numbers occur when the first derivative is 0, and then we solve this equation. When you solve this equation, you are going to need to know your log properties and your exponential properties. You do this one at a time. And then I like to order the critical numbers from left to right on a number line. So even though I got this 1 first, I noticed that 1 over e squared is less than 1. So I'm going to order this as the first critical number, and the number 1 is our second critical number. Put these on a number line and go ahead and test the first derivative. You're testing over 3 open intervals. Make sure you indicate your test values. You do this yourself, you get to choose, but you do need to pick a test value between 0 and 1 over e squared. Don't work too hard, just pick 1 over e to the third power and evaluate that into the function. Now, when you evaluate that into the function, make sure you understand your log properties and be able to execute them very, very well. You do the same thing for the next 2 intervals. Just make sure you indicate a test point or test value and then find its parity. See if its parity is positive or negative. So when you evaluate at 1 over e, or e to the negative 1, this does simplify to be this, which is negative. Once you realize that is negative, we also know that the function is actually decreasing on that interval. You do the same procedure for the third interval. Make sure you pick a number greater than 1. E would be a good choice here. E squared would also be a good choice. I picked e. Go ahead, evaluate at e. It turns out that will give you a positive output. State the intervals of increasing and decreasing. There they are. Do we have any local extrema? And the answer is yes, because the function increase and then decrease, which makes you focus on this critical number. This critical number is 1 over e squared. If your function increased and then decreased, that means we must have a local maximum. Evaluate to get that local maximum. Once again, you do that by evaluating the function at 1 over e squared. Do the same thing for the second critical number. And what do we know about the second critical number? Before that critical number, the function was decreasing, and then after that critical number, the function is increasing. That means at the critical number of 1, the local min is 0. And how do you get that? You simply evaluate f of 1. What about concavity and inflection points? That goes beyond the first derivative. Now we need the second derivative. So make note earlier that you were able to find the first derivative and then from there be able to take the second derivative. Once again, if you can factor that derivative function, do so. And if it's a fraction, make sure you could separate your numerator from your denominator so that you could find the critical numbers for the first derivative. Now, in order to come up with intervals of concavity, we need the second derivative to be continuous. For that reason, you never need type 2 critical numbers for the first derivative. We only need type 1. So if you need type 1 critical numbers for the first derivative or for the test for concavity, simply set the second derivative equal to 0 and then solve that equation. Once again, know your log properties. You get a d value. We only have a single d value for this particular example. What do we do with that d value? You place it on a number line, and then you test the second derivative around that d value. Around that d value means before the d value in an open interval, and then after that d value in an open interval. Make sure you indicate your test values. And I like to locate or note which second derivative function I use. There it is. Notice you could pick your test values in such a way that you do not need a calculator. You may have noticed that you don't need a calculator for most of calculus. It sounds ironic because you think calculus will involve a calculator, but it's not. Calculus involves mostly algebra. If the second derivative is negative, you know that the function is concave down on this open interval. If the second derivative is positive, you know that it is concave up on this open interval. Once you realize that, you may have noticed that the change in concavity took place. If the change in concavity took place around 1 over e, that means it went from negative to positive. That means that there's an inflection point. The first half of that inflection point is 1 over e. How do you find the second half? Once again, go ahead and evaluate it into the function. When you evaluate 1 over e into the function, turns out you also get 1 over e. Once you have your second derivative number line, I advise you to place your first derivative number line right below it. So this scheme here is crucial. What you're trying to do is figure out all the pieces of the puzzle. And so let me box the scheme that I'm talking about. It's right here. This scheme is so important because the first and second derivative basically indicates the turning points and the shape of your graph. Putting all the pieces together, you realize it's wise to organize all those pieces in a t-chart. And these are very specific pieces. These are specific ordered pairs that you know will lie on the function. Even this first indicator here, I wanted to remind people there is a hole at the left end of this domain. And as you are piecing this information together, everything will work out. For instance, you may have recalled that the second derivative is concave down on the interval from 0 to 1 over e. Now, breaking this up into more intervals, we know that the first derivative indicated that the function is increasing on the smaller interval here. So if it's concave down and increasing, you will then get this shape right there. Similarly, if it's concave down and decreasing, you'll get this shape right here. If the function is concave up and decreasing, you get this shape right there. If the function is concave up and increasing, you get this shape right here. This scheme right here gives you a lot of information along with this organized t-chart. Once you have this organized t-chart, do your best to scale a graph and put a sketch of this function. In this case, my scale on the y-axis is really large. I indicated 1 pretty high, but my scale on my x-axis is even larger. I indicated 1 very, very far. Putting all the pieces together, we do get what we anticipated. We have a local max, which is only a local max and not an absolute max. How do we know it's not an absolute max? We know the function increases without bound as x approaches infinity. We have an inflection point, namely 1 over e comma 1 over e, and that inflection point indicates a change in concavity. An inflection point indicates a crucial turning point in your model. And a local min is a different kind of turning point, and the local min took place when x equals 1. This, however, is an absolute min because the function increases after that local min, and there's no other minimum values indicated on the other intervals. So this is not only a local min, but that is also an absolute min. So there's an absolute min, no absolute max, but there is a local max, and there's one inflection point.